Okay, sir.
Yes, Ananta, is it possible to brief what you discussed yesterday?
Sir, we were calculating problems and all.
Yeah, we have solved one problem. Okay. After that, I discussed with some theory na, on what concept?
Delta modulation.
Delta modulation. Okay. Is it possible to say what is done in delta modulation? I have understood how analog signal is converted into digital one by using delta modulation. It is basically analog to digital converter.
Yes, sir.
So what is the advantage when compared to PCM?
Sir, it provides staircase, no, sir.
Yeah, it provides staircase waveform. Here the number of quantization levels are what? Only 2, right? So it is a 1-bit quantizer we use. But in case of PCM is not like that. We used to have a number of quantization levels. That depends on number of bits, right? If I am using 2 bits, then I will be having 4 quantization levels like this. So as the number of bits increases, the number of quantization levels also used to increase. Only thing is we may used to get more accurate sample value, but the bandwidth requirement was more. Okay, so to overcome that issue, we are going for delta modulation. In case of delta modulation, we can reduce the transmission bandwidth, and since here it is only we are using 1-bit quantizer, so the bandwidth requirement has been drastically reduced. We'll see how much bandwidth has been reduced when compared to PCM and all. Hope I think this is the strength today. Only a few people have joined. It is already 11 o'clock. Okay, then let me continue. Okay, where I stopped yesterday. Yeah, just as a recap, as I said, in case of delta modulation, we oversample the message signal, okay, to increase the correlation between the adjacent samples of the signal. So by doing so, we will be able to use the simple quantizing strategy for constructing the encoded signal. Okay. So with that, we say delta modulation provides the staircase approximation of the oversampled version of the message signal. Yeah. Yeah, as I said, the difference between the input and the approximation will be quantized with only 2 levels. Okay, that is either plus delta or minus delta, right? That depends on whether it is positive or negative differences. If it is positive difference, it will be increased by delta. If it is negative, it will be decremented by delta. Okay, so that is what I was discussing here with the example. So to just again recap what I discussed yesterday. So this dashed signal is my analog signal, that is M of t, message signal. Okay, I am going to convert that into a digital one by using delta modulation, right? So how do I do that? So I begin, means I get a staircase waveform. I will tell how do I get the staircase waveform. So to begin with, so this is my sampling interval. As I said, I sample at TS, 2TS and so on. Okay, so this will be TS. Then next one is 2TS, then 3TS, 4TS, 5TS and so on. Okay, so let me take at the beginning, this is my staircase approximated value. I compare that value with my analog input signal. Okay, now the approximated signal is greater than the analog input signal. hence it will be decremented by delta. Okay, it will be decremented by delta. So what is delta? I say that is step size. Okay, then it will be retaining that value till the next sampling interval. Now again we will compare with the analog signal. Still at this point of time also, okay, at this point of time also, my approximated signal is more than the analog input signal. Hence it will be again further decremented by delta. Okay, so it will retain that value till the next sampling interval. Okay, so at this point of time, my approximated signal is less than the analog signal, hence it will be incremented by delta. Okay, and it will be there that value till the next sampling interval. Again, it will compare at this point. Now, the approximated signal is greater than my analog input signal, hence it will be decremented by delta. Okay, it will be retaining that value till the next sampling interval. Again, it will compare with the analog input signal. Now, the approximated signal is less than my original analog signal, hence it will be incremented by delta. Okay. Again, it will be there that value till the next sampling interval. So now also my approximated signal is less than analog signal, hence it will be incremented by delta. Okay. So this process keeps continuing till the end of this analog signal. Hope this you have understood. So whenever we decrement by delta, that will be referred by binary data 0. So first two steps decremented by delta, hence it is written 0, 0. Next is incremented by delta, so it is written 1. Okay, again it is decremented by delta, so it is written 0. Like that it keeps, we denote the binary data. Okay, whenever we decrement the approximated signal by delta, we write it as 0. Whenever we increment by delta, we represent it by 1. Okay. So basically, this is just input-output characteristics of the delta modulator, what I can say. This is my input and this is the output. So delta, okay, the symbol is different. You can take it as this delta only. Okay, plus delta and minus delta. So this is how the input-output characteristics of delta modulator, what we can say. Okay. So, yeah, for better clarity and understanding, one more diagram I have shown here. I think here with the grid structure, I hope you will be able to understand this further clear. We can write this as sampling intervals as what. So this is a step size, very clearly mentioned. Right? This x of t is my analog signal, and this is my approximated signal. This u of t is my approximated signal, and this is a sampling interval, right? So you can write 0. This as 0. Then TS, right? Then 2TS, 3TS, 4TS, and so on, right? So, for example, here at this point of time, so to begin with, anyhow, my approximated signal is less than analog input signal. Hence, at this point, it will be there that value. So, it will compare at T equal to TS, right? At this point of time, my approximated signal is less than the original analog measure signal. So it will be incremented by delta. Okay. Then again it will be retaining that value till the next sampling interval. So at this point again it compares. Still at this point time, at this time also, my approximated signal is less than analog signal. So it will be again further incremented by delta. Okay. Again it will be there that value till the next sampling interval. Again it compares with analog input signal. Still at this point of time also, the approximated signal is less than the analog signal. So again, it will be incremented by delta. Okay, and it will there that value will be hold at the next sampling interval. Here also it will compare. Okay, so still here also it is less than, means approximated signal is less than the original signal. So it will be incremented by delta. Okay, so till it will be there that value till the next sampling interval. At this point time also, it is less than original analog signal, so it is incremented by delta. At this point also, still it is less, hence it is incremented by delta. So from only the first is 0, rest all 1, 1, 1, right? Next it will be there that value. Now the approximated signal is greater than the analog input signal, hence it will be decremented by delta. Okay, now that is why it is 0. Okay, now at this point also, the approximated signal is greater than my analog input signal, hence till this point, it will be further decremented by delta, right? Again, it is 0. So like this, it continues. Hope you're getting how I am saying this staircase waveform. Yes, is this picture is clear?
Yes,
Yes,
sir.
people. I think so. This is how we say, how do we get this zeros and ones with the delta modulation? Okay, now I will come to the block diagram of the delta modulation. Okay, so this is the transmitter side and this is the receiver side. So I give the sampled input signal. I denote that as M of NTS as one input to the comparator. Okay, another input to the comparator is from accumulator. I will tell about this accumulator. Okay, what it is and all. So that is what, that is the delayed version of output of this quantizer. Okay, means this one MQ of NTS minus TS is the approximated signal. Okay, MQ of NTS minus TS is the approximated signal that will be compared with my original analog input signal sample. So if the difference is positive, then what, it will be incremented by delta. If the difference is negative, it will be decremented by delta. Right? That E of NTS is the difference of these two inputs, M of NTS minus MQ of NTS minus TS. Okay, as I said, it is a one bit quantizer. So it produces an output of either plus delta or minus delta. Okay, so EQ of NTS is what, output of the quantizer that will be given as input to the delay element. Okay, that and the difference of this, that will be denoted as MQ of NTS. So that is what, this is a quantized version of the original signal delayed by one duration, that will be given as input to comparator. Okay, so this is how it works. So this we call it as an accumulator. Okay, it accumulates the present and previous samples. That is why it is called accumulator. Then output of this quantizer will be encoded either 0 or 1 depending upon the value, whether it is delta or minus delta. If it is plus delta, we denote it by 1, and if it is minus delta, it will be denoted by 0. Hope this is clear. How the delta modulator transmitter is. So what is input? I have two inputs. One input is the original signal sampled input that I denoted as M of NTS. Another input of the comparator is what? The delayed version of my quantized version of the signal. So that I denote as MQ of NTS minus TS. Then the difference of that will be given as input to the quantizer, right? So this quantizer produces an output either plus delta or minus delta depending upon the value of E of NTS. Means whether this difference is positive or negative. Okay, if it is difference is positive, then the output of the quantizer will be plus delta. If the difference is negative, then output of the quantizer will be minus delta, right? So I will be encoding that plus delta by 1 and minus delta by 0. That will be my delta modulation output. Okay. So here this feedback mechanism, what is done is output of the quantizer will be fed to the delay element. Okay. So I am denoting output of quantizer as EQ of NTS. No? That will be added with the delayed version of the quantized version of the signal. Okay. And this MQ of NTS is the what, input to the delay element. I get MQ of NTS minus TS, delayed by TS, right? That plus EQ of NTS will be input to the delay element. Okay, so I'm comparing the present and the previous sample. That is why I sample the signal at slightly higher than the Nyquist rate, so that the correlation between the adjacent samples will be almost similar. Okay, to increase the correlation between the adjacent samples, I sample at higher than Nyquist rate I used to tell, right? This is how the delta transmitter works. Okay, to understand with equations. So please note here, E of NTS is what, output of the comparator. I will go back to the equations and I say what is written here. See, E of NTS. E of NTS is the what? Output of the comparator. That will be equal to what? M of NTS. See, M of NTS is one input to the comparator. That is the sampled version of the analog message signal, right? Then MQ of NTS minus TS is the delayed version of the quantized version of the message signal. M suffix Q indicates the quantized version of the original message signal delayed by a sample interval TS. Okay, the difference of those two will be the input to the quantizer. Is this fine? E of NTS is the output of the comparator, right? So what will be the output of the quantizer? I said it is a 1-bit quantizer, right? So output of quantizer will be a delta function. It will be a step size, okay? And I can denote that as sinum of E of NTS. Why I am writing? I can write sinum of E of NTS because I have shown the input output characteristics of the delta modulator will be like this. So this we represent as sinum function. Okay, so sinum function and its magnitude is what? Delta, right? Delta into sinum function of E of NTS I can write. So that is what is written here. Output of the quantizer EQ of NTS will be step size into sinum of E of NTS. Is this fine? This equation and this equation. Then I said MQ of NTS, right? That is the input to the delay element. And what is this MQ of NTS? Is the quantized version of the original message signal. So that will be what? So from figure we will understand. So MQ of NTS, this one, MQ of NTS at this point, right? So it is what? Addition of these two, MQ of NTS minus TS plus EQ of NTS. So sum of these two will be MQ of NTS. Okay, so that is what is written here. So equations are not complex. So input to the delay element, that is the quantized version of the message signal, will be the sum of the quantized version of the delay element, that plus output of the quantizer. That will give you MQ of NTS. Is this fine? Yes, I am asking, is this fine? Is equations are fine? They are not complex, very simple to understand. So first one, E of NTS is our output of the comparator, right? That will be what? The difference of these two inputs. Yes, E of NTS. Here, output of the comparator, right? This will be difference of these two, M of NTS and MQ of NTS. Then EQ of NTS, I can write it as delta into sinum of E of NTS, right? Then this MQ of NTS will be sum of these two, MQ of NTS minus TS plus EQ of NTS. That is what is written there. Okay. And this is the demodulator circuit, means here we do analog to digital conversion, right? So this has to do reverse process, that is digital signal will be the input and it has to convert that one to analog one, right? So that is what is called digital to analog decoder. So actually it is a decoder, not encoder. Okay, it is a decoder. So I think there is a print mistake. Okay, it is a decoder. So this DM wave will be given as input to the decoder. Then there will be an accumulator. Okay, so means one input to accumulator is the DM modulated signal, that is decoded waveform. Another one is delayed by 1 bit duration. Then output of that will be passed through a low pass filter. So to get back the original analog message signal. I will say in detail about this. Okay? Before. Hope delta modulation transmitter is clear. Yeah, I think. Okay, if this is done, then I think I need not again say what is the. It is all just explanation what I have told there. Okay, that means what the delta modulator will have and all. Okay, I said TS is the what sampling period, and E of NTS I am saying is the error signal, that is output of the comparator, right? That will be what the difference between the present sample. Present sample is what M of NTS. Of the input signal and the latest approximated signal. Latest approximation is what MQ of NTS minus TS. Okay, then EQ of NTS is the what quantized version of the E of NTS. Okay, then I said the quantizer output EQ of NTS will be finally coded to produce the delta modulation signal. Yeah, I think you can have a look about this. Just I said it has comparator, right? Quantizer, then accumulator, how they are connected and all I said. So comparator means this quantizer, we say it consists of hard limiter, means it is basically sinum function, right? So which I have told already, the sinum function. Then the quantizer output will be applied as an input to the accumulator. So So I can write this MQ of NTS is delta into summation of I is equal to 1 to n sin m of E of I into TS, where the value of I can vary from 1 to n. Okay. Then that can be written equivalently as EQ of I into TS. Okay. Or EQ of n into TS also. Okay. So you can, yeah, means how do I get plus delta, minus delta and all is already explained that. I think I need not again repeat the same thing. So here, let me say a few things about that staircase approximation, right? Yeah. So in case of delta modulation, okay, there are two types of quantization errors. Two types of quantization error. Similar to the PCM, there also we had some quantization error, right? So which is equal to, we used to write delta squared by 12. Similar to that, here also we have two types of quantization error. One is called slope overload distortion. Okay, another one is the granular noise. Let us see what is that slope overload distortion and what is granular noise. Okay, so I will go to that issue and I will explain it. Yeah, to explain that both the noises. So this example is fine. Okay, so here what we are finding, here we are finding a steep increase in the input signal, right? Right. But the staircase waveform will not be able to follow or track the steep change in the input signal. Okay, there is a gap. There is a gap of the staircase waveform from the analog input signal, right? So this we call it as a slope overload distortion. Because to keep track of this steep change in the analog input signal, what we need to do is we need to increase the step size, okay, and as well as the sampling frequency or sampling period. Then only it is possible to track the change in the input signal. Means if the input signal changes very fast, what I mean to say, okay. Hope people are understanding what I'm saying. So here what we are finding is when the input signal changes very fast, okay, since the step size is fixed, in case of delta modulation, the step size is fixed, so it will not be able to track the original analog input signal, okay. So there is a gap, okay. So if at all I want to keep track of this, what I need to do, I need to increase the step size, right? Means I need to make the step size variable, right? Because here in case of delta modulation, what I said is the step size is fixed. Because of that, there will be a gap between this approximated signal and the original analog input signal. Okay, so that is known as the slope overload distortion. So I can overcome that by increasing the step size and as well as the sampling period. Okay, and another case is whenever there is no much change in the input signal, okay, during that time, means this portion of the signal, what happens if I increase the step size, it will be hunting between those two values only. Means either, since the input signal is not changing much fast, right? But the output of the delta modulator will be oscillating between two values, either plus delta or minus delta. Okay, so that is known as the granular noise we call. Okay, so here the selection of step size, that is delta, and the sampling period TS plays an important role in achieving proper delta modulation. Okay, one is a step size, another one is the sampling period. Okay, so if I increase the step size, I can overcome this slope overload distortion, but at the same time, if there is no much change in the input signal, then it will be exhibiting the granular noise. Means it will be oscillating between plus delta and minus delta. That I said it is a granular noise, right? So the selection of step size and the sampling period plays an important role in the delta modulation. Okay, so that is what is told here. Yeah. So to keep track of that original input signal, right, what we need to do is we need to set this step size, and the sampling period should be greater than or equal to maximum rate of change of analog input signal. Means how, at what rate the input signal changes now, this step size and the sampling frequency has to be greater than the rate of change of input signal. Then only it is possible to keep track of that steep change in the analog input signal. So this condition has to be satisfied, right? So to satisfy this, okay, if I vary the step size, right, means if I increase the step size, as I said, there will be a granular noise. Okay, so let me read this. Okay, yeah. So what we have seen is the digital approximation to the derivative of the input signal, or equivalently can say inverse of the digital integration process. Okay. So if you consider the maximum slope of the original input waveform m of t, it's clear that in order for the sequence of samples, that is MQ of NTS, right, to increase as fast as the input sequence of the samples m of NTS in a region of maximum slope of m of t, we need to satisfy this condition, right? Otherwise, we find that the step size delta will be too small for the staircase approximation. Okay, so that results, okay, that MQ of t falls beyond m of t. MQ of t is a what? Approximated signal, right? So that condition is known as the, I said, slope overload distortion. Okay, is that fine? Okay, so to make this approximated signal, okay, to follow the analog input signal, we have to change the step size. So as step size increases, okay, fine, and decreases, this MQ of t tends to occur along the straight lines. So because the step size is fixed here in case of delta modulation, we call that as a linear delta modulator. Okay. So another case, what I said, granular noise, right? What is it, granular noise? So when the step size delta is too large, okay, too large compared to the change in the slope of the input signal, in that case, what happens? The staircase approximation MQ of t will be hunting around the flat segment of the input waveform, right? So that phenomena is known as the granular noise, I said. So that is what is shown here, right? This is a flat, right? There is no much change in the input signal. So during that time, the staircase waveform will be hunting between two values, plus delta and minus delta. That I said it is a granular noise. And this will be our delta modulated signal. How do we represent that 0 and 1, right? So here it is 0, rest all it is 1, 1, 1. That is why it is written with high. Then they're all zeros from here to here. That is why it is written with 0. Then again here 0, 1, 0, 1, 0, 1 will be there, right? Fine. Yeah, the same thing shown with one more diagram. I hope I took this from the net. I think this is from the textbook. You can write any one diagram to explain the concept of the quantization error in the delta modulation. Okay. Only thing is you should keep two types of errors in the quantization errors in the delta modulation. One is what? Slope overload distortion, and another one is the granular noise. So when do we get the slope overload distortion? Whenever there is a steep change in the input signal. See, I hope you will be able to understand this, right? There is a steep change in the input signal. Then this staircase waveform will not be able to track or follow the steep change in the input signal because the step size delta is fixed, right? So to follow that, I need to vary the step size and as well as the sampling frequency. Okay, so that a difference is known as the slope overload distortion. Difference between the staircase approximated signal and the original message signal. When there is a steep change in the message signal, so that is known as a slope overload distortion, right? Then, as I said, whenever the analog input signal is not changing at all, okay, means it is constant, right? So since if I increase the step size, right, so this delta here, it is oscillating between only two values, either plus delta or minus delta. Okay, once it may be 1 or it may be 0, like 1 0 1 0 1 0. That we call it as a granular noise. Okay. So large step size, okay, if I increase the step size to overcome the slope overload distortion, then what I said, I will be facing this granular noise, right? If the step size is small, then I will be facing the slope overload distortion. Means I will not be able to track the original analog input signal. So the accurate value of delta selection is an important challenging task in the delta modulation. So there's what is written here: choice of optimum step size. Okay, that will minimize the mean square value of the quantization error in the linear delta modulator will be the result of the compromise between the slope overload distortion and the granular noise. Okay, so to improve the performance, we need to make the delta modulator adaptive, isn't it? Means how the input signal changes, accordingly I need to vary the step size. Then I will be able to minimize these two errors and I will be able to improve the performance of this delta modulator. Okay, so that is known as the adaptive delta modulation. Okay, that is why it is called. Means when we make the step size adaptive, right? So the step size is made to vary in accordance with the input signal. That we call it as a adaptive delta modulation, I said. So do you have any doubts regarding this slope overload distortion and granular noise? So these are the two different types of errors which occurs in delta modulation. And I said why slope overload distortion occurs also I said, and what is granular noise. If you have any doubts, you can ask. So again, I need not say about all these things. So it is self-explanatory. Yes, any questions? So this is all about delta modulation, what I can say. And it is very, very important also. So definitely they will ask about these two errors. Okay. And maybe the concept of delta modulation also. Yes, any questions to ask? Or is it clear? Or you have not understood anything at all? Yes, students, you should open up your mouth and say, if you have understood, I will go further. Or if you want me to explain once again, I can explain. Yes, what is your opinion or understanding?
So understood, sir.
Understood. Okay. So then shall I go further? Okay, so next one is the delta sigma modulation. Okay, delta sigma modulation. So let me say what is the drawback of the previous linear modulator. Already I told what is the drawback, right? So here the quantizer output in case of conventional delta modulation, right? Whatever I discussed so far, right? The quantizer output in the conventional delta modulator may be viewed as an approximation to the derivative of the incoming message signal. Quantizer output means that is EQ of NTS, okay, will be equal to what? The approximation to the derivative of the incoming message signal, that is d by dt of m of t. Okay, so that behavior leads to the drawback of what? Delta modulation in the transmission disturbances like noise, okay, that result in accumulative error in the demodulated signal. So to overcome the drawback, instead of as what we are saying here, it is a derivative of the incoming signal, right? In case of conventional delta modulator. So we replace the drawback by integrating the message signal, okay, prior to the delta modulation. Okay, then we will be able to overcome that problem. So that is the block diagram what we find here. I think I will go to the directly block diagram and I will sell. Yeah. So this is the see what we have done here in the earlier case, the message signal, right? We used to sample it and then we used to compare that with the previous approximated quantitative version of the signal, right? Here, what we do in the previous case, I said the message signal is as good as, means the quantizer output will be as good as the derivative of the message signal. So here, what we do, we pass this message signal through an integrator. Okay, then that integrated signal will be compared with the approximated signal. Then the rest of the things are same. Okay, here quantizer will be there. Then this is for making the steps as variable. Okay, so that whatever accumulator part was there, that accumulator part is replaced by an integrator. Okay, in case of conventional delta modulation, we have written accumulator part, right? That is a delay element along with that adder that has been replaced by an integrator. That's all. Okay, rest of the things are same. Then this is about the receiver part. This is, so this part is transmitter part, and the receiver part, same thing. What we use a low pass filter, then we get the estimation of the message signal. Okay, so that is the difference. Okay, what is the difference? We integrate and then compare when compared to the conventional delta modulator. So with that, we will be able to overcome those problems. Okay. Yeah. Okay, so that, as we were saying, the noise will be accumulating the error in the demodulated signal. To overcome the problem, what I said, we do the integrating message signal prior to the delta modulation. Okay, so the use of integration will be having certain benefits. Okay, first thing is the low frequency content of the input signal will be free emphasized. Okay, integrator is nothing but a high pass filter. Is it so?
How, sir?
No, that's what I'm asking. Can I say integrator is a high pass filter or low pass filter? It is basically a low pass filter. Integrator is a low pass filter. Okay, differentiator is a high pass filter. Because integrator means we write here capacitor, a resistor, then we take output across the capacitor, right? It is basically a low pass filter circuit, no? Yes or no? Hope understanding what I'm saying.
So this is integrator, sir.
No, this is integrator circuit only. Oh, you're having doubt. See, if I use op amp, then it becomes active integrator. Means op amp is an active element, right? It is an integrator circuit only. So I use capacitor in the feedback, right? And then resistor in the input side. Okay. So means it will pass only the low frequency components. High frequency will be eliminated, right? Because as the frequency increases, the reactance of this capacitance decreases. Yes or no? X is equal to 1 by 2 pi Fc. As F increases, the reactance becomes reduces, no? Means it acts as a short circuit. So high frequencies will be nullified. Means it will be connected to the ground. In that sense, I say it is a low pass filter. So hope it is clear.
So just repeat what you said.
See, Xc is what reactance, no? Xc is equal to what I write? 1 by 2 pi Fc, no? Xc is equal to 1 by 2 pi F into C, right? So as F increases, when F equal to 0, so 1 by 0 is what? Infinity, na? Means reactance is very large. Means it acts as a open circuit. Capacitor acts as open circuit. So I get output is equal to input. Right? So as F increases, then reactance decreases, right?
Yeah.
So when the reactance decreases means what? It becomes a short circuit, right?
Yeah.
The reactance of the capacitance decreases means it becomes a short circuit, means it will be grounding the high frequency signal. So hence I say it is a low pass filter. So integrator is a low pass filter. Okay. So with the integration, the low frequency content of the input signal will be pre-emphasized. So already you know what is pre-emphasis, right? A boosting of the low frequency signal. So with that, the correlation between adjacent samples of the delta modulator input is increased. So we will be able to improve the correlation between the adjacent samples of the input signal. So with that, we will be able to improve the overall system performance, okay, by reducing the variance of the error signal, okay, at the quantizer input. And even the design of the receiver is also simplified, he says. So the delta modulation, which incorporates integration at its input, is known as the delta sigma modulation. Okay, delta sigma modulation. Hope you'll be able to understand the difference between just delta modulation and then delta sigma modulation. So in delta sigma modulation, the input signal is fed through an integrator to the comparator. Okay, that should be there. And I said what is the advantage of using integrator also. It is also known as sigma delta modulation, right? Sigma delta modulation, because the integration is performed before the delta modulation. Okay. So here the message signal is defined in its continuous time form. Right? We feed M of T only, not M of NTS. We are not going to discretize the signal. We feed the continuous time signal only to the integrator. But in the earlier cases, means in case of delta modulation, we used to do the sampling first. Okay, so input is M of NTS, not M of T. That is another difference. I will come back to this. Okay, means pulse modulator now consists of this hard limiter followed by a multiplier, right? And that multiplier is given as another input as the what external pulse generator that will be used to produce 1-bit encoded signal. Okay. Yeah, pulse generator we use to encode the output of this hard limiter. Means hard limiter is nothing but what? It is the quantizer only. Okay, the symbol indicates quantizer only, 1-bit quantizer. And this pulse generator is used to encode the output of this hard limiter. Right? So this is the, yeah, this is another way of representing the same thing. Okay, equivalent version of delta sigma modulation system. So message signal means he has interchanged the integrator and comparator. Earlier case, integrator was earlier, then comparator. Now he has taken integrator inside. Okay, there is a difference. Rest all same only. First he compares and then he do the integration, and he is eliminated the integrator in the feedback. Hope you are able to understand. Here, two integrators are used. Okay, before comparator one integrator, and in the feedback also one integrator. So same thing is replacing one integrator in the feedback and connecting output to the comparator, then he does the integration. Okay. So I think you can write any one or you can write both equivalent circuits. Okay, I think this I said. What is that? Let me say about this one. So the use of integration, right, at the transmitter input, it says clearly requires the inverse signal, right, namely the differentiation at the receiver side, right. So the need for this differentiation is eliminated because of its cancellation by integration in the conventional DM receiver. Okay, so the receiver of the delta sigma modulation consists of simply a low pass filter. That is why. Okay. So this receiver will have only low pass filter. We don't have any, means in case of conventional delta modulation, we used to have, I think I will show this diagram. Yeah. So we used to have decoder, then this accumulator, then low pass filter, right? So this has been eliminated because we use the integration in the transmitter side. So that is what the receiver part becomes simple. Hope understood this point. The use of integration at the transmitter input clearly requires an inverse signal emphasis, namely the differentiation at the receiver side, right? So the need for this differentiation is eliminated because of its cancellation by the integration in the conventional DM receiver. So the receiver of a delta sigma modulation consists of only a low pass filter, okay, which I have shown there. Okay, what I wanted to say is basically the integration is a linear operation. So we may simplify the design of the transmitter by combining the two integrators, 1 and 2, okay, into a single integrator placed after the comparator. So which I have already told with respect to this block diagram. Okay, so in the previous block diagram, we have two integrators. So we can combine these two integrators and use only one integrator after comparator. So that is what is done there. So this delta sigma modulation is not only simpler than the previous one, but also provides an interesting interpretation of delta sigma modulation as a smooth version of the 1-bit pulse code modulation. Okay, the smoothness refers to the fact that the comparator output is integrated, right, prior to the quantization. Right, comparator, then integrator, then quantizer is there, right? So that is why we say the smoothness refers to what? The comparator output is integrated prior to quantization, and this term 1-bit pulse code modulation I said na, is related to the quantizer. Okay, it consists of hard limiter with only 2 representation levels. Yes, is that fine? It's able to understand, no? This hard limiter means 1-bit quantizer it is. 2 representation levels, one is 0 and another 1. Okay, we integrate the output of the comparator and then we give that as input to the quantizer. Okay, yeah. So hence it is known as 1-bit PCM. Okay, 1-bit PCM, this delta sigma modulation. Okay, the reason for investigating delta modulation is its what? Reduced bandwidth, as I was telling in the beginning only, as compared to the PCM, right? As I said, in PCM, the transmission bandwidth required is more. Okay, so it's given in what way, how much it is reduced with the example. So in case of telephone application, the PCM system uses 8 kilohertz sampling rate with 8-bit representation with an overall binary symbol rate of 64 kilohertz, means 64 kbps. Okay, but in case of, if I use instead of PCM, if I use a delta modulation, how much bandwidth will be reduced? So it uses 1-bit representation level, right? And it will be oversampling the signal. So with that, the oversampling rate of delta modulation will range from 16 to 32 kilohertz. Okay. So in case of PCM, we sample the signal at 8 kilohertz. Though the message signal is at 4 kilohertz, that is 3.4 kilohertz, we slightly round it off to 4 kilohertz and we sample at 8 kilohertz. With that, we require 64 kbps, or we can say 64 kilohertz is the bandwidth, right? But in case of delta modulation, though we do the oversampling, and that oversampling rate is from 16 to 32 kilohertz. Okay, so depending upon the voice quality, right? So by using delta modulation, it is possible to save the bandwidth of around 50 to 75% over the PCM, right? Only the thing is, the circuit complexity is more compared to PCM. Okay, at the expense of more complicated implementation. So this is what the advantage of delta modulation, what I wanted to say. And to be very specific, here it is told to what extent it is reduced. Okay. Yeah. So this is about differential pulse code modulation and all. So in addition to PCM, even we can go for a differential pulse code modulation, whereas that technique is combination of delta modulation and the PCM. Okay. Okay, anyway, we are not discussing what is differential pulse code modulation, even adaptive differential pulse code modulation and all. That is the next version of that. So with respect to that, what we wanted to say is, means those things are used in the vocoders. Vocoder, are you aware of that? What is vocoder? That is voice coder and decoder. Okay. So more advanced voice coding or vocoder techniques make use of the correlated nature of the voice samples to reduce the bandwidth requirement even further. Okay, so the techniques uses the process of 10 to 30 milliseconds voice spurt to construct the model of the voice spurt, and it may be communicated to other end with just few bits. Okay, so with that, with a standard 64 kbps, which is required for PCM, can be reduced as little as 2.4 kbps. Okay, 2.4 kbps, depending upon the voice quality that is acceptable. So where is 64 kbps and where is 2.4 kbps? You just think the amount of bandwidth which is able to reduce, okay, with the acceptable quality of voice. Fine. So this is how advancements have been done in the analog to digital converters. Yeah. So with this, what I can say, this delta modulation topic I completed. Only I think 2 more case studies are there. We'll have a discussion about that. Hope we'll try to implement. I can show you by using MATLAB also, since we are doing it for 7th semester lab. Not an issue. If you are interested, in the next class, I will show with MATLAB code also how this can be implemented. Okay. Is that fine? Yes, any questions to ask, you can ask. So for this third test, 3 models will be there. Okay. 3, 4, 5. Hope people have submitted their OB activity